09
Yep.
of Rutgers, PhD 09, currently at the University of Quebec at Montreal. We'll talk about congruences for algebraic sequences. This is also, even though it's official colloquium, it's also cross-listed as the experimental math seminar and as all our seminars, so it can be uploaded into Vimeo and be available online. These talks, you can always watch it again. Also, since it's also experimental math seminar, the rules apply and no multitasking, and you cannot use your laptops or electronic devices. So I just want to point it out. But the only exception is the duration is 52 minutes instead of 48. Let's go.
All right, well, thank you for the invitation, and thanks everybody for coming. I want to talk about congruences for algebraic sequences. So here's the outline. We're going to talk about what algebraic sequences are, which should be pretty painless. Then we're going to talk about automatic sequences, which maybe some of you haven't seen before. And then this will lead us into diagonals of rational power series, and finally a bunch of congruences for algebraic sequences and other sequences that I'm able to get with this method. And I should mention this is joint work with Reem Yassawi, who's at Trent University. So, what's an algebraic sequence? A sequence of integers is algebraic if its generating function is algebraic over q of x. So, meaning that it satisfies some polynomial. And these sequences occur all the time in combinatorics. One of the main examples is the Catalan numbers, which is this sequence right here. The nth term of the Catalan sequence it counts all sorts of things. For example, it counts the number of lattice paths where you're allowed to step up and to the right and down and to the right. And you want to walk from the origin to, let's say, 2n comma 0 for the nth term. So here n will be 3 since we're walking to 6 comma 0. And using only those two types of steps, and you never go below the x-axis. So for n equals 3, there are 5 different paths, and here they are here. And this is the sequence in general. There happens to be a closed form for the nth Catalan number in terms of binomial coefficients, but this is not really going to be relevant to us. The only relevant thing is that this generating function satisfies this algebraic equation. That's a quadratic equation. So the Catalan numbers are a main example. Another main example is the Motzkin numbers, which sort of lurk around usually when you have Catalan numbers. And they're also defined, they also count lattice paths and all sorts of other things. For example, the number of paths that start at the origin and go to n comma 0, now where you still have the same two steps, you're allowed to go up and to the right and down to the right, but you're also allowed to just stay constant. And there are 3 different steps now. And there are 4 different paths for n equals 3, so m of 3 is 4. And this is also an algebraic sequence. This generating function satisfies this polynomial equation. So there are lots of sequences in combinatorics that are algebraic. I just want to mention a few others. The Fibonacci sequence is algebraic. In particular, the Fibonacci numbers satisfy a recurrence with constant coefficients, and so you get a rational generating function, in fact. So of course it's rational, so therefore it's also algebraic. And if you have any integer value polynomial, a of x, then evaluating a of x at the positive integer, the non-negative integers, gives you a sequence that also has a rational generating function. So algebraic sequences include these more familiar sequences. Okay, so here's the main question I want to ask. Pick some prime power, p to the alpha, and we want to know if we take an algebraic sequence of integers, what does it look like when we reduce every term modulo p to the alpha? So Deutsch and Sagan sort of launched a minor industry in 2006 with a paper in which they looked at Catalan numbers and Motzkin numbers and all sorts of other things, Reardon numbers, and et cetera, et cetera, et cetera. Central binomial coefficients, central trinomial coefficients turn out to be algebraic sequences. I don't know, probably 10 other sequences they looked at in this paper. Modulo very specific prime powers, so modulo 2 and 4 and 8, and a few small other primes, 3 and 5, I think. And so that's where this sort of minor industry came from. They start off their paper by considering the Catalan numbers modulo 2. So here's the sequence of Catalan numbers again. Here they are mod 2. And if you look at that for a minute or so, it's not too hard to guess that it looks like we have 1s roughly spaced out as powers of 2. And it turns out that Cn is odd precisely when n plus 1 is a power of 2. So this was known. I haven't traced this back as far back into the literature as it was known. It was known at least in the 70s, probably way before that. And Deutschland gave a combinatorial proof, that's very specific to this particular sequence.
No, but for the 2n to the n, it's classical.
Right, and you can also, since the Catalan numbers have this formula, I don't know how classical, I mean, maybe in Dixon's theory of numbers, I haven't checked. But yeah, it's certainly been known for a while. So this is sort of a very basic example. We get sort of the characteristic sequence of the powers of 2, basically, for the Catalan numbers mod 2. Okay, so in this paper, like I said, they looked at Catalan numbers modulo 2, modulo 4. One of the more interesting results was a conjecture that they attributed partially to Teddy and de Verhan, who, and this conjecture gave necessary and sufficient conditions, conjecturally of course, for the nth Motzkin number to be divisible by 4. And so here's the first few Motzkin numbers again. And they also conjectured that no Motzkin number is divisible by 8. So a few years later, this was proved by Yu Liu and Ye in 2008. They proved not just the fact that Motzkin numbers are never divisible by 8, but also this necessary and sufficient condition for them to be divisible by 4. And this is about a 20-page paper in which they first write the nth Motzkin number as a sum of Catalan numbers, and then use the particular closed form formula for the Catalan numbers to get arithmetic information about Catalan numbers modulo 4 and 8, and then sort of translates that back up to Motzkin numbers. So it's a very ad hoc approach, very specific to this to the Motzkin numbers and Catalan numbers. And so I was interested in seeing if there's a more general way to produce such things. So in particular, what these guys did, they determined Cn mod 4. So and here it is. So the nth Catalan number modulo 4 is 1 if n is 1 less than a power of 2, which is sort of what we saw before for Cn mod 2. We saw that it's 1 precisely when n plus 1 is a power of 2. And then it turns out that you never have a Catalan number congruent to 3 mod 4. And this maybe isn't obvious just by the definition. Well, I don't think it's obvious at all, just as a huh?
Then it follows Catalan number is 2n to the n minus 2n to the n plus 1. And for the non-coefficient, it goes back to very, very old, to Luca, to Kummer. So it seems to me this will follow from classical stuff, like the Pascal triangle.
I don't know. I haven't thought about that particular question, but I would be a little bit surprised if it was that easy. Maybe it is. I don't know. I mean, with Catalan numbers, you have a lot of leverage because you do have this nice binomial coefficient.
Yeah. No, for Catalan, it's Catalan.
Yeah, this is Catalan.
No, Motzkin, I'm not saying Motzkin.
No, Motzkin, yeah.
But Catalan to me,
okay, it might, maybe. Yeah. So these guys still took a lot of work to pull this out. Not a lot, but it took several pages to write this. So the other thing is to decide whether it's 2 or 0 mod 4, and it's 2 if n can be written like this. So sort of what we had before, but an extra power of 2 written out there. And they also determined Catalan numbers mod 8, and I didn't want to retype this, so I just copied this from their paper. So, but what I want to point out is that basically it's the same sort of conditions. You look at whether n is a certain combination of powers of 2, etc. So 2 years later, 2 of those co-authors put out another paper in which they determined the value of the nth Catalan number modulo 16, which I reproduced here. This is sort of getting to these sort of messy nested piecewise function. Again, all these little functions that are appearing, I don't want to define them, but they're all operations on the base 2 representation of n. So that's the important part. And they also determined Cn mod 64, which spanned over several theorems. And I'm not going to reproduce that here. Okay, so the point so far, what we've seen is that at least for a small alpha, the nth Catalan number modulo 2 to the alpha seems to be directly computable from the base 2 digits of n. So the base 2 digits of n really reflect the structure of the sequence. And so we would like to know whether a similar thing holds for other, namely first for other primes, and then for other algebraic sequences and other sequences more generally. And then, of course, this other question is, do we really, is this the kind of thing that we're going for, or is there a more natural way of representing these things and storing them? Okay, so I want to mention one. This is one little detour, which is that and Mueller developed the first systematic method for producing congruences for algebraic sequences and more generally some subset of the class of holonomic sequences. The caveat is that it only works in their first paper from last year. This only works for powers of 2. And then just last month, they had another paper that's, this one was 80 pages long, and this is also 80 pages long. And basically, they replaced all the 2s with 3s, but so it's not. It hasn't been extended to work for an arbitrary prime yet. And the way it works is that you consider this generating function, which is transcendental over Q. Modulo any power of 2, this actually satisfies a polynomial equation. And so what the industry is, what their methodology is figuring out what the minimal polynomials for this thing are modulo powers of 2. And then of course they have to redo all that work for powers of 3. But you get this sort of thing. You get here's the generating function for the Catalan numbers, and modulo 64, it's congruent to this sum of powers of this phi of z, where the coefficients are Laurent polynomials. All right, so I think this is better notation. This is sort of more natural, closer to things that we like to deal with than all these piecewise functions.
1 over z in some of those coefficients.
Yeah, right. So yeah, what's the explanation there? So they either cancel each other out, or yeah, I don't know. Yeah, in general, their theorems have Laurent polynomials as coefficients. Yeah, so I don't know the explanation of that, but it must be something fairly simple. Okay, so what I'm going to talk about is
it's mod 64, so maybe it becomes a negative.
Yeah, so mod 64, yeah, it's possible that when you expand all these powers of phi, it must be the case that they cancel out, that those terms.
There's 0 mod 64.
All right, so what I'm going to talk about is a class of sequences called automatic sequences, which I believe is really the natural way to frame these questions. So let's look back at this theorem of Yu and Ye about the nth Catalan number mod 4. So it says that the nth Catalan number is congruent to 1 mod 4. Let's use a chalk. Here we go. If n is 2a minus 1. So, and 2a minus 1 in binary, of course, just looks like this because a power of 2 is 1 followed by a bunch of zeros. So this is 1, and looks like this. And then what does the second expression look like? Well, it's 2 if n has a bunch of 1s like this, but then has some set of zeros, and then a single 1 following it, right? So this 2 to the b is this is in the b position or something like that. So, and then 0 otherwise. So the idea is to take the binary representation of n and process it. It doesn't really matter in one direction. I'm going to start with the least significant bit and process it to the left, and come up with and write a graphical machine, which will be this, that determines that the output of this machine will give you the value of Cn mod 4. Right. So how does this machine work? There are 4 states, which are these 4 disks, and the arrows tell you how to transition between the 4 states. So this unlabeled arrow says that this state is the initial state. So we always start here. And then we read in a digit one at a time. And when we read a digit, we follow the edge that's labeled with that digit. So when we read the string of 1s, every time we read a 1, we just follow this loop, and we always stay in this state. And whatever state we're in, when we finish reading the full binary representation of n, there's a label associated with each state, and so that becomes our output. So reading a string of 1s, again, we just stay in this state, this one state, and once we're finished, we're still in the state, so we output 1, which corresponds to this one. So if we start seeing a 0, as soon as we see a 0, we enter this state, and then we read a bunch of zeros, but no binary representation of a number ends in a 0. So this isn't a terminal state. Eventually we have to see another 1 again, and then we are in this state. And if that's the end of the word, then the output is 2, which it should be according to this theorem. And then anything we see after that, as soon as we see another 1 after that, then we're in this state, and after that we always stay in this state, and so the output is 0 otherwise. So this graphical machine is an equivalent way of phrasing this piecewise function. And this machine is called the deterministic finite automaton with output. The finite is the important part. The automaton is just the machine. Finite is the fact that there are only finitely many states, and so you only need to keep finite memory around at any one time when you're evaluating one of these sequences. Okay, so sequence is k automatic if there's a deterministic finite automaton with output, whose output is the nth term of the sequence when you feed in the base k digits of n. So we just showed that this sequence, using that theorem of u and yet, we just showed that this sequence, Cn mod 4, is 2 automatic because the nth term is produced by a finite automaton when you read the base 2 digits of n. And notice that k-automatic sequences are always on finite alphabets because we only have finitely many states, and each state corresponds to some output, so there's only finitely many possible outputs. So you don't tend to look at k-automatic sequences of integers. You tend to look at k-automatic sequences of elements in a finite field or residue classes or something from some finite alphabet. So probably the most famous automatic sequence is the Turing-Morse sequence, and the nth term Tn is the number of ones in the binary representation of n mod 2. So it just tracks the parity of the number of ones in the binary representation. Here's the first few terms, and this is 2 automatic because it's given by this automaton where we start at this state. Initially we've seen an even number of ones, and then every time we read a 0, it doesn't change the parity. So if we've seen an even number and we read a 0, we still see an even number, and if we've seen an odd number and we read a 0, we still see an odd number, and every time we see a 1, we flip the parity. So the 2A Morse sequence is given by this finite automaton. The 2A Morse sequence's claim to fame is that it's cube-free, meaning that if you think of this as an infinite word on a binary alphabet, there's no subword that occurs 3 times consecutively. And this is one of the very early constructions in combinatorics on words in 1906 or something like that by 2A. And it was rediscovered several times. It was rediscovered, and if you can use the sequence to there's some rule in chess that says if you have the same repetition of moves 3 times in a row, and then it's a draw or something, and or something, is that right? And so you can use the sequence to show that there are infinite games of chess, even with this rule.
They changed the rule because of that.
Oh, really? Okay. So no longer then. The characteristic sequence of powers of 2. We've already sort of seen this. But again, if you're reading in, if you want to detect whether a string of 0s and 1s represents the power of 2, you're reading a bunch of 0s. As soon as you see a 1, that's fine if that's the end of the word. But if you see another 1, then it's not a power of 2 anymore. And a fun one is the sequence that gives solutions to the Tower of Hanoi puzzle. So the Tower of Hanoi, you have some stack of disks, and you want to move them all from one peg to another peg. There's 3 pegs that you can use, and the rule is you can only pick up 1 disk at a time, and you can never place a larger disk on top of a smaller disk. So the minimal solution for a fixed number of disks, is just some finite word, of course. On the set of possible moves. The set of possible moves are, take a disk from peg 1 to peg 2, take a disk from peg 2 to peg 1, so I think there's 6 different possible moves. And so you can specify the minimal solution as some word on this 6-letter alphabet. And so if you let the number of disks go to infinity, then you get this infinite word, and it turns out to be 2 automatic. You can compute the nth term by feeding the base 2 digits of n into some finite automaton. So automatic sequences have been studied extensively. There's a very good book by Jean-Paul Alouche and Jeff Shalit. I just want to mention that it was already known in 1960 that eventually periodic sequences are automatic for every k, which is maybe not obvious. So if you take a sequence that is periodic with period 5, you can still produce it by feeding the base 2 digits of n into some finite automaton. And they're really natural things. So they come up maybe more in computer science than mathematics, but I think they deserve to be better known in mathematics than they are. And there are several natural characterizations. So for example, the one that's really going to be important is this algebraic characterization, which says that if you have elements, if your alphabet is the finite field of size p, then a sequence is p-automatic if and only if its generating function is algebraic. So p-automatic sequences, over a finite field, p-automatic sequences and algebraic sequences are exactly the same thing. Well, okay, a finite field at least of size p. A similar thing works for other finite fields. So this immediately implies that if we take an algebraic sequence of integers and reduce them modulo p, we get a p-automatic sequence. Because, so here's the Catalan sequence again. So I'm going to take the coefficients and reduce them mod p. I'm also going to reduce the coefficients in the polynomial mod p, so mod 2 in this case. So this sequence, if there had been a 2 in front of all these coefficients, then this would have been 0. But barring bad cases like that, then what we'll get is a generating function with entries in the field of size 2 that now satisfies this polynomial equation. And by the Crystal theorem, since it's algebraic, it's therefore 2 automatic. Right, so automatic sequences over a finite field are precisely the algebraic sequences. And the proof is constructive. It's basically linear algebra if you know how to set up the right system. And so you can take a polynomial like this and just automatically crank out an automaton that will produce the nth term. So this tells us about primes. This tells us that if we have any algebraic sequence of integers, reducing mod p will give an automatic sequence. So it's some sequence that's produced by reading the base p digits of n into a finite automaton. But this doesn't say anything about prime powers, and so it won't say anything about the Catalan numbers mod 4 or anything, even though we've already seen that is an automatic sequence. So here's where diagonals of rational power series come in. Okay, what's a diagonal of a rational power series? Well, a diagonal of a general power series in multiple variables is just what you would think. It's a univariate power series where we set all the indices equal to each other. So it's just sort of, if we think about all the coefficients in a big finite dimensional array, then it's just the diagonal of that array. And in 87, Dennett and Lipschitz showed that if you have two polynomials, so this is going to be a rational function, with coefficients that are p-adic integers, or if you prefer, you can say that they're integers, such that the constant term of the denominator is invertible mod p, and that's really just so that we have a nice unique power series expansion for this rational function r over x. So basically, if you have a nice rational function and you look at the diagonal, so you get this univariate power series, and you reduce it mod p to the alpha, any prime power, then the sequence is p automatic. All right. I want to give just a very short proof sketch. This is a very sketchy sketch in the bivariate case, so just two variables. So we let d be some digit in base p, and there's this thing called the Cartier operator, which is a map on formal power series. It's a very simple map. What it does is it takes a formal power series and it just takes an arithmetic progression of terms. So it takes every pth term starting at the dth term. So it's a very simple operation. And then what you do is you say let S be this set of diagonals. So this is a set of all diagonals mod p to the alpha of certain rational expressions. You have a q to the p to the alpha minus 1 in the denominator, and the numerator is bounded in degree by some n that I haven't told you. But the point is that this is a finite set because this degree restriction limits you to only finitely many numerators. And then you show that this set is closed under this Cartier operator, so that when you take any element in here and you index, take the arithmetic progression sub-indices, you still end up with an element in here. And the initial sequence that you're interested in is in here because, well, here's the initial sequence that we're interested in. We can just multiply the numerator and denominator here by some power of q to put it in this form. So the original sequence is in S, and S is closed under the Cartier operator. And so what you end up doing is then drawing, you have p different Cartier operators, one for each digit. And so what's going to happen is we just let each of these diagonals be a state in the finite automaton. And course, you're not actually carrying these around as infinite power series. You're just carrying these around as rational expressions. And we just draw an edge labeled D from one of these diagonals to another if one is the image under the Cartier operator of the other. Right, so I'm skipping lots of details here, but this is the basic idea. There's some finite set of rational expressions running around, and you can build the automaton directly out of that. So let me just show you the theorem once more. So this is the theorem. So if we have a rational expression with some mild condition on the denominator, then taking the diagonal and reducing mod p to the alpha gives you a sequence that is produced by a finite automaton. Okay, so this says something about diagonals of rational functions, but of course, if we're interested in algebraic sequences, this doesn't help us at all. But there's a nice proposition of Furstenberg from the 60s that says if you have an algebra, it tells you basically how to transform certain algebraic sequences into diagonals of biury rational functions. So if we have some polynomial, again, this can be the integers if you like, some polynomial where the derivative at the origin with respect to y is not 0, and the constant term of the power series is 0, and the power series satisfies this polynomial, then constructing this crazy rational function by taking the derivative of this polynomial that the generating function satisfies, and then plugging in x, y for x, and blah, 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 sticking in a few y's, the diagonal of this thing turns out to be the sequence that you started with, the power series that you're interested in. So this gives you a way to turn algebraic power series into diagonals of rational functions. All right, so the main algorithm then is to take some polynomial satisfied by the power series that you're interested in, check that the constant term is 0 and that this derivative is non-zero mod p, and then use this Furstenberg proposition to convert it from an algebraic sequence to the diagonal of a rational function in two variables, and then use the Dennis-Lipschitz theorem to compute an automaton for the coefficients of f of x mod p to the alpha. And of course, these conditions don't always hold, so I'll get back. This one's sort of mild, right? It's only going to fail for as long as this isn't 0, it's going to only fail for finitely many p. And this one we can fix usually. So if these two conditions hold, then this is purely mechanical, and we implemented it in a computer program. And then we could just, take any algebraic sequence and any prime power and generate automata all day long and see what answer questions that we may be interested in. For example, are there forbidden residues? Like no Catalan number is congruent to 3 mod 4. So this is very easy to check because once we have an automaton, we just look, well, if there's no output, if there's no state that corresponds to the output 3, then this automaton can never output 3. So it's very easy to check. We can compute the limiting distribution of frequencies when they exist, how many Catalan numbers in the limit are congruent to 1 mod 4 and 2 mod 4, or 0 mod 4. We can tell things like whether the sequence is eventually periodic, and just apply all this theory that's been built up for for automatic sequences to these sequences of residues mod prime powers. All right, so this is a long overdue example. So here we have again the Catalan numbers, which satisfies this algebraic equation. And here's what I was talking about before, right? Our condition here, back the slide, was that the constant term of the power series was 0. So we don't have that because the first Catalan number is 1. But it's not a big deal. We just shift it, pretend that it's 0, and now we're looking at a slightly modified power series where it's now just agrees with the Catalan numbers for n greater than or equal to 1. And this modified power series satisfies this polynomial equation. We check this partial derivative. It's non-zero mod 2, so we just run the machinery. Furstenberg's proposition tells us that this power series is the diagonal of this rational expression, and we can use that to compute this finite automaton for Catalan numbers mod 4. So notice this isn't the same one we had before. This has 6 states, and the other one we had was 4 states. So this in general won't give you the minimal automaton, but that's okay. It's still an automaton, and if you're really interested in the minimal automaton, there are algorithms to minimize automata. All right, so like I said, we can do this all day long, and so I spent several days doing this all day long, and here are the results. So part of it, I mentioned that Liu and Ye determine Catalan numbers mod 8 and 16. Well, here are the automata for Catalan numbers mod 8 and Catalan numbers mod 16. And just by, again, just by looking at all these states and saying, oh, well, there's no 9 that appears, then that's a proof that there's no Catalan number that's congruent to 9 mod 16. And here are Catalan number, here are forbidden residues for Catalan numbers modulo higher powers of 2. Right, and so,